Hi guys, this video that I'm going to make now, it again concerns college level students who may be preparing for IIT JAM or GATE or JEST. This specific video concerns quantum mechanics. In this video, I'll try to prove the following. I'll try to prove that the time derivative of the expectation value of linear momentum equals the negative of the expectation value of the gradient of potential energy. Now, this is something that is reminiscent of classical mechanics. This almost says that force is equals to the negative of the gradient of potential energy. In fact, this is probably as close as we can get to classical mechanics using quantum mechanics. But in case of quantum mechanics, if we try to get to classical mechanics, this suggests that we will have to use expectation values rather than the actual values uh, of the quantities. So in a sense, it is the expectation values that follow classical mechanics. So let's try to prove this. First of all, we need the definition of expectation value. The expectation value of any operator, but in this specific example, I need the expectation value of the momentum operator. In Dirac's bracket notation, it will be like so. The definition, of course, holds for any operator, but I'm using it only for the momentum operator. The expectation value of the momentum operator is the momentum operator sandwiched between the states, the ket state and its corresponding bra state. The name ket and bra, they come from the ket vector and the bra vector. If we combine them together, we form the bracket or the bracket. So that's how the names come. If I do not use Dirac's bracket notation, I can explicitly write out the integral. If I write out the integral, it becomes psi star px cap acting on psi, and the integral has to be done over entire space, so it's a volume integral extending from minus infinity to plus infinity. So this is the expectation value of the momentum operator if I explicitly write out the integral. Now, what I need is the time derivative of the expectation value of momentum. So if I do that, if I take a time derivative here or a time derivative here, what I can do, instead of writing the derivative outside, I can take the derivative inside the integral. It's called the differentiation under the integration sign. It's a very common property. So this is equals to, if I take the derivative inside, if I take the time derivative inside, I can use the product rule. So this becomes d psi star over dt px cap psi plus psi star px cap d psi over dt, and the whole thing is a volume integral. Of course, I don't differentiate the momentum operator because the momentum operator has no explicit time dependence. Therefore, the time derivative of the momentum operator doesn't exist. It has no explicit dependence on time. Most operators that we encounter in quantum mechanics have no explicit time dependence, just like the momentum operator. So this is what we have to calculate. To calculate this, first of all, what I'll need is the Schrodinger equation. If I write down the Schrodinger equation here, minus h bar squared over 2m grad squared psi. Of course, I'm writing down the Schrodinger equation in 3 dimensions, plus v psi gives I h bar d psi over dt. If I take the complex conjugate of this equation, I get minus h bar squared over 2m grad squared psi star. So if I take the complex conjugate of an equation, I change all the psi's to psi stars and I change all the i's to minus i's, plus v psi star equals minus I h bar, because this is the complex conjugate of the Schrodinger equation, d psi star over dt. I change all the psi's to psi stars and all the i's to minus i's. Now, looking back here, if you know anything about quantum mechanics, you know what the momentum operator is. The momentum operator is defined to be minus I h bar ddx. So, if I substitute the expression of the momentum operators here, what I get is this. In place of px, I replace this. The minus I h bars are constant, so I can take them out of the integral sign. D psi over dx plus psi star d squared psi dx dt. This of course becomes a double derivative, first differentiated with respect to time and then with respect to x. So this is the thing that we have to calculate, and obviously the entire thing is inside a volume integral. Now coming back here, using the Schrodinger equation, taking the complex conjugate of the Schrodinger equation, I got this. I need another thing. I need an expression for this. To get this, I can differentiate the Schrodinger equation with respect to position. If I do that, I get minus h bar squared over 2m grad squared d psi over dx. Of course, the order of differentiation doesn't matter, so I can always differentiate psi with respect to x and then take its Laplacian, plus to differentiate this term with respect to x, I need the product rule. So first I get this term v d psi dx, and next I get psi dv dx, and on the right hand side I get I h bar d squared psi over dx dt. So now, using this and this, I can begin substituting them. The expression for this comes from here, and the expression for d psi star dt comes from here. I can as well take the minus I h bars in. So if I do that, in place of minus I h bar d psi star dt, I can write down this entire thing, which is minus h bar squared over 2m grad squared psi star plus v psi star, all multiplied with d psi dx. There's another term coming from here. For this, I can write psi star multiplied with the negative of this, because here there's a plus IH bar, here there's a minus IH bar. So taking the negative of this, I can write minus h bar squared over 2m grad squared d psi dx plus v d psi dx plus psi dv dx. And the whole thing is inside a volume integral which goes from minus infinity to plus infinity. To proceed, let's see if anything cancels from these. I think this term v psi star d psi dx should cancel with minus psi star v d psi dx. So I can cancel this and this. Of course, I can only cancel them after I expand them, but since I'm working with limited space, I won't bother doing that. I'm cancelling them directly from here. So v psi star d psi dx cancels with minus psi star v d psi dx. After this, let's start grouping terms. Let's group terms with grad squared in them. So if I do that, I get from minus infinity to plus infinity. Remember, it's a volume integral which extends from minus infinity to plus infinity. It includes the entire three-dimensional space. Minus h bar squared over 2m grad squared psi star, this multiplied with d psi dx. I've only written down this term multiplied with this, minus grad squared d psi dx multiplied with psi star. Let me make it, turn it into one integral. So I'm writing out the integrals separately. There is another integral, and that involves this term. For that, I can write minus integration minus infinity to plus infinity psi star dv dx psi, and the whole thing is a volume integral. Now, if you realize, this thing is just the definition of the expectation value of the gradient of the potential energy. So for this, it's just simply minus of, the minus of course comes from here, the expectation value of dv dx. Now see what we have to prove. We have to prove this. So this equals this, that is this. But in trying to calculate, in trying to figure this out, we have now got two terms, this and this. But we have to show that this is only equal to this. So this must be 0 somehow. This has to be 0. If we can prove that this is 0, we are done. So to that effect, let me erase all the things that I do not need anymore. To try to prove, or to try to move ahead with this, I'll use two identities. The first one is like so, grad dot psi star grad of d psi dx is grad psi star dot grad d psi dx plus psi star grad squared d psi dx. This is just one simple identity that I'm using. Another identity that I will use is grad dot d psi dx times grad psi star. In a very similar way, this becomes grad d psi dx dot grad psi star plus d psi dx times grad squared psi star. Now if I take the difference of these two equations, these two terms will cancel out. They are the same. So taking the difference of these two equations, I can write grad dot, of course my nablas are vectors, I'm not writing them out explicitly, psi star grad d psi dx minus d psi dx grad psi star. This equals, these two terms have cancelled out, so this equals this minus this, so we can write psi star grad squared d psi dx minus d psi dx grad squared psi star. So, taking the difference of these two equations, we get this equals to this. Now if you compare this with what is here inside, I think they are the same. They are one and the same. Perhaps there is only a difference of negative sign. Well, if I compare this with this, there is only a difference of negative sign. So if I take this minus sign inside the integral, now this part of the expression is the same as this. They are both same. Therefore, this integral, this integral, if I rewrite this integral, I can now write integration from minus infinity to plus infinity. Let me take the h bar squared over 2m out of the integral. Grad dot, in place of this, I can now substitute this. Psi star grad d psi dx minus d psi dx grad psi star, and the thing is a volume integral. Now, what we can do to proceed from here is that we can use the divergence theorem. So what does the divergence theorem say? The divergence theorem says that integration over some volume grad dot, say some vector f, this is equals to integration over the surface that encloses this volume, this is f dot dA. So the divergence theorem basically relates the volume integral with the surface integral. All you have to remember if you use a divergence theorem is that this surface is no arbitrary surface. This surface is the surface that encloses this volume. So using divergence theorem, I don't think I'll bother to write h bar squared over 2m any longer. If I use divergence theorem, I get psi star grad d psi dx minus d psi dx grad psi star, this dotted with the area vector. This is now a surface integral which goes from minus infinity to plus infinity. It's a surface integral which goes from minus infinity to plus infinity. Well, which surface is that? It is the surface which encloses the volume. Now, if you notice, all the integrals were from minus infinity to plus infinity. That has to be so because we have to include the entire three-dimensional space. Therefore, the volume that I was talking about is a volume at infinity. It's a volume that covers the entire three-dimensional space, and it extends from minus infinity to plus infinity in all directions. Therefore, the surface in this integral is a surface at infinity. And psi star, they both go to 0 at infinity. They have to go to 0 at infinity, otherwise the wave function won't be normalizable. For the wave function to be normalizable, they have to fall off to 0 at infinity. And so they do, because the surface is a surface at infinity. Therefore, this entire integral collapses to 0. Let me repeat once again. This integral collapses to 0 because this is a surface integral and the surface over which I integrate is a surface at infinity. Because this surface has to enclose this volume which extends from minus infinity to plus infinity in all three directions. And therefore the surface is a surface at infinity. And the wave function falls off to 0 at infinity. Therefore this entire integral goes to 0. So we started out with this, and moving ahead step by step we saw that this is actually a sum of two terms, this and this, but we have now shown that this equals to 0 using the divergence theorem. So what we are left with is this equals to this. So our proof is done, and as I said, this is probably as close to classical mechanics as we can get using quantum mechanics. Thank you.